All right, in this lesson, we are going to look at applications that involve writing a regression equation. And so we are going to be choosing between linear, exponential, and quadratic. Okay. And sometimes it's not always the best fit to the points as much as it is to the trend of the data. And so looking at number 1, we are talking about population. It says the table shows the US population in millions of people at 20-year intervals from 1815 to 1975. Okay, and so it says create a scatter plot of the data. We will do that in Desmos. Then use Desmos to determine an exponential regression. Okay, so they're telling us what to use. Find the value of the correlation coefficient. And then define, write, and sketch a function to model this situation. Okay, and so when you are working with a table of points that has years, you might want to define your X column to be years since 1800. And so that way you're not typing in these big X values. It won't show up on your graph. So we'll do 15, 35, 55, 75, 95, 15, or 115. And then 135, and then 155, and 175. So years since 1800. Okay, so those will be our X's. And then remember, this is in millions of people, okay? And so in Desmos, always make sure you're using test practice, and if you want to choose an assessment, choose Texas Star. That's what you'll use on your test. Okay, and so click the plus sign, add your table. We're going to do 15, 35, 55, and it's already predicting what we want. And then we have 8.3 million. 14.7, 26.7, so the first thing I want to do is kind of see if I can find the points on the graph. Because those X values are so large, we're going to have to zoom out quite a bit. And so you can see our points are following an exponential curve. And so because it's trending up, a lot of people would say that looks quadratic and try to choose quadratic. But think about population. It would be starting at 0 and growing. It's not going to start high, go low, and then back up. So quadratic isn't going to be best fit for this situation. So think about what you're trying to model. And so they also told us to use exponential. And so up in the blue, right underneath the plus sign where we clicked table, you'll see a line with dots. Click that. And so don't choose linear, choose exponential. And our equation is y equals 8.08 times, and I like to put it in parentheses, 1.02 to the x. Okay, and you can see it graphed the exponential equation in black. So it's not ideal for going through all the points, but it does fit the situation and what they asked us to do. Okay, so it says state the domain and range of the function you sketched. Because it's exponential, the domain is technically all real numbers, but for real world situations, we don't look at anything less than what we what would make sense. And so if we're talking about time, our domain would go from 0 to infinity. And then for our range, because this exponential function has a horizontal asymptote at 0, it would go from 0 to infinity and never actually reach 0. Okay, and so next it says, use your function to predict the population in 1990. And so for 1990, that's not on our table, and so it would fall right in between the, it's not on our table, and so it would fall after the 1975. And so what we can do is treat that as our x value, and so our x value, years since 1800, would be 190. And so in Desmos, there's a couple ways to do this. Because we have our graph, our black graph, you can just go underneath and type x equals 190. X equals 190. And then it's going to graph a red line where the 190 is, and you would just click where it intersects our model. And so that gives us the point 190 and then 370. And since our table is rounding to the nearest 10th, I am also going to round to the nearest 10th. And so our predicted population would be 370.5 million people. Okay, for our next example, we are looking at a frozen can of soda. It says a 12-ounce can of soda was put into a freezer. The table shows the volume of the soda in the can measured at different temperatures. Okay, and so it says use a graphing calculator to create a scatter plot, sketch the plot. We won't actually sketch it, but we will use Desmos. And so get your Desmos. And then plus sign table. Put your X's. Now, as you were typing in these y values, you may have noticed that they are very, very close in value. They're ranging from about 354 to 356. So something that may be helpful for us is to press this tool and kind of adjust our values to match the table. And so it looks like the smallest value is 14. So we could say 10 for the x. And then the largest value seems to be 68. And so we'll go to say 70 for now. We can always zoom out. For the y, it looks like our smallest value is still above 354. And so I'm going to do 354.5. And then it doesn't go above 356. So I'm going to try these and see if we get a better value. Okay, and so here's our graph. And so it kind of looks like it is reaching a minimum and then kind of going back up. And so when we click our regression, we're thinking quadratic would likely be the best. That's the only function that goes down to a minimum and then comes back up. And so exponentials are either always increasing or always decreasing. And then linear is always increasing or always decreasing. And so quadratic is the only one that is both. Okay, and so we are going to choose quadratic. And then we are going to write our equation, y equals, and then 0.00085 x squared minus 0.069 x plus 356.31. Okay, and now it says predict the volume of the soda can when the temperature is 20. And so something else I didn't point out in the last example, look at the r squared value. It's really close to 1. The closer you are to 1 or -1, the better this is for your data. Okay, and so because that's close to 1, I know this is a good fit. If I choose exponential, that r squared value is not close to 1. It's practically 0. And then linear typically also works for quadratic, but in this case, you're seeing an r squared value really close to 0. And so quadratic is going to be a clear best fit. Okay, so now it says predict the volume when the temperature, so temperature, remember, is our x, is 20, and then predict for 60. So we're going to plug in x equals 20, we're going to plug in x equals 60. So while we have that graph there, x equals 20 would give us the point 2355 point, and our table is keeping 2 decimal places, so 26. And then when I plug in 60, we get 355.21. Okay, and so to answer their question, the volume for 20 degrees Fahrenheit would be 355.26 cubic milliliters. And then for 60 degrees, it would be 355.21 cubic milliliters. And so you can see how this would be hard to do on a multiple choice test because these values are so close together. If both of those were options, you wouldn't know which one to pick for each one. So it's really important that you know how to do this yourself in Desmos. Okay, on this third example, we have a whole paragraph of information, and so we kind of skip that and look at what it says. The table shows the results based on many trial runs. So we're talking about car speeds and length of skid marks, okay? And so we're gonna write, it's asking us to write a linear regression, a quadratic regression, and an exponential regression equation, and then we'll determine which one fits best, looking at the r squared value. Okay, and so going to Desmos, click table, type your x's, okay, and so clicking the regression symbol, my linear regression is, let's keep 3 decimal places for each one. So we have y equals 5.536x minus 152.444. Okay, and then look at the r squared value because that's the only value quadratic has, so we're just going to keep looking at the r squared value. And so that is 0.9 we'll keep 2 decimal places for that because we're going to see how close. Actually, let's keep 3 just so we can see which one's the best. So we have 0.97. I'll go ahead and keep all 4. Okay, and then switching to quadratic, we have 0.034 x squared plus 0.955 x minus 26.645. And then we have an r squared value of 0.9995. That's looking pretty good. See if we can find the points. That means it's going through a lot of the points. Okay, and then we'll try exponential. Looks like we missed quite a bit of the points. Our equation is 31.365 times 1.026 raised to the x. And we have an r squared value of 0.976. Okay, and so if we're picking the regression equation, we would choose quadratic. For a couple reasons, is highest r squared value or closest r squared value to 1. And then also model or graph goes through most of the points. Okay, for our next example, we are looking at community service. It says a group of students went door to door collecting donations for a local charity. The table displays the number of donations received for various donation amounts. Okay, and so it says analyze the data and list 3 observations. And so one thing I notice is as the x values increase, the y values are decreasing to 0. They don't decrease to a minimum or ever go back up. And so y values are always decreasing. Another thing I notice is that they don't get below 0. And then a third thing I'm noticing, if we look at the pattern, it looks like we're decreasing by 40, decreasing by 40, decreasing by 40, decreasing by 40. And so y values decrease at a constant rate. Of 40. Okay, and so if we're trying to choose a regression equation, we already know it would be linear because of the constant rate. It says explain why the regression models the data, because we have a constant rate. Okay, and so the reason why it's not going below 0 is because this is a real life application and we're not going to have negative number of donations. But usually when you see that, you would think exponential because it has the asymptote, but the constant rate gives away that it is linear. Our x's are going up by 1 and then our y's are going down by 40. Okay, and so when we're writing our equation, we already know our slope is negative 40x. And if we wanted to find our y-intercept, we could keep the pattern going and then just add 40 as we go backwards. And so we can see that the y-intercept would be 480. And so we could write negative 40x plus 480. And then if we want to check it with Desmos, We can add our table. I'm just going to type some of the points. Well, might as well. It's always best practice because if it's not perfectly linear, you would want all the points to get the best equation. Okay, and so we get negative 40x plus 480. All right, for this last example, it says which regression would work best for the table. So let's just put the table in and then see which of our equations looks the best. And so I've already put in the data. And we're going to compare the r squared values. And so for linear, our r squared value is 0.96. For quadratic, our r squared value is 0.9973. And then for exponential, we have an r squared value of 0.9919. And so it looks like quadratic is going to be our best model. And so we'll keep 3 decimal places for each one. So 0.402x squared minus 1600.282x plus 1593. 498.2. These numbers would be better if you did years since 1900, but we just typed them in as is. And so y, r squared value is closest to 1.